In this revolutionary era, from microcontrollers to the screen you're currently using to watch this video, every single electronic component uses strings of zeros and ones to keep track on the data. But did you know that one day it would be impossible to use a component less than or equal to the size of an atom? At the microscopic level, one particle can be presented multiple places simultaneously, and creating a quantum superposition, it can bounce through walls from one place to another. That restricted us from performing complex mathematical problems with subatomic objects on traditional computers and led to the invention of a fundamentally different technology, the quantum computer. A quantum computer uses qubits or quantum bits that can be both 0 and 1 at the same time. Now, an electron has two states, spin up and spin down, which is basically its orientation in a magnetic field. Consider this magnetic bar as an electron. If you hold it freely, it will automatically align its direction because of Earth's larger magnetic field. To change its orientation, we have to put energy from this side, just like this. The same thing needs to happen to put an electron in superposition. When placed inside a transistor, it remains in its 0 or down state because of its magnetic field. However, by hitting the electron with a very specific microwave pulse, one can create an exact position in between the two states. And that creates a quantum superposition. As qubits work basically on probabilities, the spin could be in any direction. It could be here, here, or here. However, when we try to measure it, the whole superposition collapses into one probable state, either 1 or 0. But when it comes to the calculation part, the superposition qubits can connect with each other and predict their partner's probability, and that's called quantum entanglement. This means when entangled, if we find one electron's spin as up, we can be sure that the other one's spin is down. And as the qubits show multiple spins at once and can communicate with each other, it creates a vast computational space for us. For example, this police officer is trying to find a prisoner from these 5 cells. And to do that, he has to open every door one by one and look inside to see if there is a person. But if the police officers were made of quantum objects, they could have stood in front of these 5 doors parallelly, and one of them might have found the prisoner and informed the others. By doing this, they are not only eliminating the other 4 possibilities but also reducing the calculation time by avoiding intermediate steps towards the conclusion. And then, after manipulating the probabilities with quantum algorithms, collapsing the superposition and assigning the quantum information into regular bits, we can measure the outcome on our classical screens to solve outstanding mysteries. Quantum computers aren't the future of today's classical computers. Instead, they're the vehicle to explore a totally different world. It wouldn't be wise to think of a quantum computer as our future binge-watching smartphone or tablet. Thank you for watching.